Okay, so let's continue with our sort of refresher of basic linear algebra. And last time we had ended with the definition with the definition of a basis of a vector space. Now, let me state this proposition, which I won't prove, which is, I'll make a few remarks about that, but here's the statement. So, theorem. Let V as usual, all our vector spaces are subspaces of some Euclidean space, be spanned by R vectors then dimension of V less than or equal to R. Now the point here is that as we know, there's a fundamental relation between the number of vectors needed to span a vector space and the number of maximum number of linearly independent vectors inside that vector space. In fact, that's what this proposition is sort of elaborating on, that if a vector space can be spanned by R vectors, then there cannot be more than R linearly independent vectors inside the space. The proof of this is the same as the proof of the fact that any two bases have the same number of elements. So this is the so-called replacement argument, which one sees in a linear algebra course. So I'll skip this, but instead, so if you're interested, you can look at Rudin. Instead, let's look at some corollaries and other facts. So corollary is that dimension of R is equal to n. This is immediate since we know that the standard, the set of standard vectors E1 up to En spans Rn, and so we know the theorem would tell us that there cannot be more than n linearly independent vectors, but since E1 up to En are linearly independent, we know that the dimension is exactly equal to n. All right, so the next thing is so suppose dimension of x equal to n, since I've already used n for the dimension of this subspace, I have to use a different dimension for the ambient space. I will call it Rk. X is a subspace of Rk. Well, a set of n vectors, this n is the same as the dimension of the subspace. A set of n vectors in X spans X if and only if the set is linearly independent. Again, for this statement to be true, it's essential that the number of vectors is the same as the dimension. This is a very useful thing, this statement we just made. Namely, if you want to check, for instance, if a set is a basis and we happen to know the dimension already somehow, then if one has to check two things essentially. First, look at the number of elements in that set. That if that is equal to the dimension, then we can either check whether the spanning property holds or if they are linearly independent. We don't have to check both. That's the content of the statement. Part B is the fact that every basis has the same number of elements. If B is a basis, then B has n elements. And part C is the fact that you can start with any linearly independent set in the X and enlarge it to get a basis. If X1, XR, a subset of X, is linearly independent, then there is, so let's call the set S, then there is a basis of X containing S. Again, this is once we have the previous theorem, all of these things will follow quite easily. So in fact, the previous theorem that if it is spanned by R vectors, then dimension less than or equal to R, which involves the replacement argument. That is the main thing in preliminary linear algebra. Once one has that, pretty much everything else is a corollary of this. So again, I'll skip the proof of this. So it's there in Rudin. You can have a look at this. So let's move on to linear transformations. So next thing is linear transformations. So X and Y vector spaces. Again, these are for our purposes. For our purpose, it's enough to take X and Y to be subspaces of some Euclidean space. But I won't keep mentioning that, so I'll just write X and Y vector spaces. A function actually, what mapping? The term function is used in various contexts in mathematics when the target is, when the range is R, the set of real numbers. Though strictly speaking, a function can be between any two sets. But in real analysis, especially when if the target is not assumed to be R, then one says mapping. A function t from x to y is a linear transformation if t of x1 plus x2 is t of x1 plus t of x2 for all x1, x2 in x, t of cx equal to ct of x for all c in R and x in x. So there are various remarks to be made. As usual, in any category, there are trivial examples of linear transformations. One is the zero transformation, t of x equal to 0 for all x is linear, and then the identity transformation is linear. Two, this is a useful thing to know. The second one is that a linear transformation is completely determined by what it does to a basis. In other words, so if b equals x1, xn is a basis of x, then t is determined by the set of vectors tx1, xn. So in fact, the reason is quite simple. So if x is any arbitrary vector in the domain, then I can write x as a linear combination of x1, x2, xn. So I'll write as ci xi I equal to 1 to n for some real numbers c1 up to cn. Once I write it like this, t of x by linearity is ci t of xi. So since we already, if we know what is t of x1, etc., then I know what is t of x. I just have to use the same coefficient ci. In fact, for this statement to be true, I don't even need this x1, x2, xn to be a basis. It's enough that x1, x2, xn spans the domain vector space capital X. This statement would still be true. However, if this B is actually a basis, so apart from the spanning property, if I know that right, so even if we just had the spanning property, the statement would be true, but if in addition we know that this B is a basis, then in fact we can, and we are given a set of vectors y1 up to yn in capital Y, we can use this prescription here to define a linear transformation by this formula. And the point is that the basis property, the fact that this x1, x2, xn are linearly independent, will ensure that this is actually such a linear transformation is well defined. So that's the second remark. The third one is that if T from X to Y is bijective, in other words 1 to 1 and on to, then T inverse from Y to X is automatically linear. And so now let's state the following fact theorem. Before this, I should make a definition. A linear transformation from a vector space to itself is called a linear operator. So here's the fact theorem. The linear operator T from X to X is injective. Injective is synonymous with 1 to 1. If and only if it's surjective and onto, if and only if it is surjective onto. So So the point is that when we have a linear operator, to check if it's, so in other words, what it's saying is that if it's injective, it's automatically surjective, therefore it will be bijective. So to check bijectivity of a linear transformation of a linear operator, it's enough to check that it's either injective or surjective, which is a nice thing, because in general, the definition of bijectivity involves two conditions. Here we are saying only it's enough to check one, if the domain and the target vector spaces are the same and the mapping is linear. So again, I'll skip the proof of this and then move on. So let's make some more definitions. Here the let Lxy be the set of all linear transformations from x to y. This itself becomes a vector space. Then Lxy is a vector space. Here I have to deviate from my usual, I've been sort of emphasizing that all our vector spaces are subspaces of Euclidean spaces. Now, of course, that's true for this Lxy as well, but it's not convenient to think of it as a subspace of some Euclidean space. So rather abstractly, one can, for instance, if I want to talk about, when I say that there is a vector space, I have to talk about two operations on this vector space: the vector addition and scalar multiplication. So for that, there is a natural way of adding two linear transformations. Namely, if I take T1 and T2 in Lxy, then T plus T2 is a new linear transformation. So I define it in the obvious way. Its action on a vector x, I define it to be T1x plus T2x. Similarly, scalar multiplication, I define rather C times T is a new linear transformation, and it's defined by Ct of x, C in R. So these are obvious ways of defining the operations on Lxy, vector space operations on Lxy. And with these two operations, it's easy to check that Lxy itself becomes a vector space. So for that, of course, since we are not invoking any ambient Euclidean space, to say that this is a vector space, one has to use the formal definition of a vector space, which is that there are two operations and certain properties hold. So the existence of an additive identity, additive inverse, distributivity over scalar multiplication, and so on. All those things can be checked. Then the other thing is that, so still staying with this Lxy, there's another very useful thing.
So now, in fact, let's go to x and y are Euclidean spaces. Let's take let T in L Rn and Rm. So linear map between Rn and Rm. We define the norm of T by, this is usually called the sup norm. There are various ways of defining a norm on this set of, on the space of linear maps. So this is one which is very convenient to work with. So we define it by, the sup norm is defined by norm of T is, if I look at sup norm of Tx, and this sup is taken over all vectors x with norm less than or equal to 1. So notice that the norm, I have used the norm notation here on the right hand side in two places, here and here. They are in two different Euclidean spaces, and the norm of a vector in an Euclidean space is the usual norm. It's the Euclidean norm or Pythagorean norm. So let me just quickly mention that if x equals x1, x2, xn, norm is just sum of their squares of the coordinates and then the whole thing, square root of the whole thing. So those are the two norms, but in different Euclidean spaces, which are used in the right hand side. So the basic inequality which makes this useful is the following. Note that norm Ax, or rather we're saying using T, so norm Tx less than or equal to norm T multiplied by norm x for all x in that domain. Where, of course, this norm T is what we just defined, the sup and so on. And this follows immediately from the definition, because after all, what is norm T? So the reason is norm T is sup norm Tx where norm x less than or equal to 1. Well, the only thing is that here in the right hand side I have to insist that norm x less than or equal to 1 for this to even make sense. Actually, there's another issue which I didn't address. I'll come to that in a second. But let's but if I take an arbitrary x, let x belong to Rn, then we can look at the unit vector x divided by norm x. Now, the norm of, so that would be something which I can use here on the right hand side, because its norm is exactly equal to 1 and I allow all vectors less than or equal to 1. So therefore, if I take t of this and then norm of this, since the left hand side is a sup of the right hand side, anything on the right hand side will have to be less than or equal to the norm t. So therefore, this will be less than or equal to norm t. But this 1 over norm x is a scalar and I use linearity. So I'll get this times this less than or equal to norm t. Now, this is just a t of x is just a vector in a Euclidean space, and this is scalar, and we know that the Euclidean norm, I can always bring out the scalar. So usually with an absolute value sign, but here it's positive anyway. So I can write the left hand side as this times norm tx less than or equal to norm t, and then that immediately implies this thing here, what we wanted. I just bring norm x to the right hand side. So let's stop here. Now, as I said, there was one point which I didn't mention that I'll address in my next lecture, which was that this definition, for it to make sense, I need to know that this thing here on the right hand side here is actually finite. If norm x less than or equal to 1, I need to know norm tx less than or equal to 1. So I'll come to that next time. Okay, let's stop here.